Let's look at a few more examples of cations and anions electron configurations. So if we were to look at fluorine and find fluorine on the periodic table, its atomic number is 9, it would be 1s2, 2s2, 2p5. Well, if we look at fluorine, its closest noble gas is neon, which would have one more electron. So we're going to add one more electron, and then that 2p5 becomes 2p6. So we then make F minus. That is the anion that fluorine will become. It's fluoride. It wants to gain one more electron. So we then make that F minus, and its electron configuration is 1s2, 2s2, 2p6. Let's look at sulfur. Sulfur, atomic number 16. And sulfur's closest noble gas is argon at 18. So we know that sulfur wants to become a -2 anion. So we can see that we would write its electron configuration as S. So 1s2, 2s2, 2p6, 3s2, 3p4. And we know that we want to add 2 more electrons to make it S minus 2. And so to add 2 more electrons, that 3p4 becomes 3p6. Again, remember, this should be the same electron configuration for argon. So S2 minus is isoelectronic. Same, iso means same, electronics, electron, same number of electrons as argon. Let's look at Na. Sodium's atomic number 11, and it would be 1s2, 2s2, 2p6, 3s1. You know, sodium is the first element in that third S shell. And we know that sodium wants to get rid of that one. We know everybody in the alkali metals gives away an electron. So that means to become Na plus, we have to get rid of that 3s1. So we can see here we would then have an Na plus, which is equal to 1s2, 2s2, 2p6. And if you look back, that would be the same electron configuration as the nearest gas, which is neon. How about Ge, germanium? It's atomic number 32, and it is going to end, it's in the 4th shell, and it's in the P block. It's the second P. Here we go. So we can see that it's the argon, and then in brackets, 3d10, 4s2, 4p2. Well, germanium wants to become a 2 plus ion. That means it's going to get rid of 2 electrons. Well, which 2 is it going to get rid of? The highest 2. Going to get rid of that 4p2. So we're going to have Ge2 plus, so argon, 3d10, 4s2. And then let's look at titanium. Titanium is also in the 4th block, but it's in the 3d2. So we've got 3d2 and then of course the 4s2. Again, it wants to get rid of the highest, which would be that 4s2, cross that off. So then we would have titanium 2 plus and then argon in brackets 3d2. Let's do some practice. Why don't you pause this real quick and look at these. What's the electron configuration of phosphide, which is P -3? And hopefully you went and looked that phosphorus is atomic number 15. Its closest noble gas before it, so we were looking at the noble gas configuration. Before it is neon, so we'd have neon in brackets. And then phosphorus wants to become, we're going to go back here. Phosphorus wants to become like argon. That's the closest noble gas. So it wants to gain 3 electrons. So it was 3p3. Now we're going to have 3p6. So how about this one? What's the electronic configuration for selenium with a 2 minus charge? So take a minute, pause. So selenium must become like krypton, and krypton's going to be either Kr brackets or argon's noble gas before it, so that would be in brackets, and then 4s2, 4p6, 3d10. How about what's the electronic configuration of bromide? Pause. And yes, bromide wants to become like krypton. We could also write it argon, and then 4s2, 3d10, 4p6. How do we know these electron configurations of ions? Well, one important source of evidence is the study of the magnetic properties of matter. Ions that have unpaired electrons are paramagnetic, so they are attracted to a magnetic field. Substances in which all electrons are paired, so those two electrons of each pair, remember they have opposite spins, experience a slight repulsion when they're in a magnetic field. So they are diamagnetic. And again, that's without unpaired electrons. Let's look at an example where we are drawing these orbital box diagrams and looking at the ions that they form and whether or not they are paramagnetic or diamagnetic. Looking at this, we want to look at the electron configurations for vanadium 2+, 3+, and then cobalt 3+. So let's look at V. And normally, vanadium is going to be, let's see, argon in brackets. And then we are 3d3 and then 4s2. Again, that's not lowest to highest energy. Remember, lowest to highest energy, especially looking at the periodic table, we know that going from left to right, we would say 4s2, 3d3. However, when we're doing, looking at becoming ions, we are losing our highest N first. So I'm going to draw this, and we're going to look at 3D, 1, 2, 3, 4, 5. This is my 3D, and then this is my 4S. So I've got 3D3, 1, 2, 3, and then 4S2. This is V just as a neutral atom. But if I'm going to become a +2 ion, that means I'm going to give away 2 electrons. So V2 plus would look just like this with 3 unpaired electrons. Paramagnetic. If I wanted 3 plus, that means I'm going to give away 3 electrons. So I just gave away 2 here. We're going to give away 1 more. So I would have 2 unpaired electrons. Again, paramagnetic. Let's look at cobalt. Cobalt is in that same row. So I'm going to write cobalt up here. Argon, and then 3D, 1, 2, 3, 4, 5. This is my 3D, and then 4S. We know 4S2, and then cobalt is 3D, 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. And we want cobalt 3+, so we're going to take off 4s2, one of those, and then we have to take away one of the doubled up pairs. And that's the one that after we each do single, then we go back and double. So we got to take away one of those doubles. So cobalt 3+ would look like this and have 1, 2, 3, 4 unpaired electrons. So also paramagnetic. Let's do a little bit of checking. Write the electron configuration for the cations potassium and arsenic with a +1 and a +3 charge. So potassium plus 1s2, 2s2, 2p6, 3s2, 3p6, and it would be isoelectronic to argon. And then actually this arsenic 3+, if you tried working through it, hopefully you saw that arsenic would not want to become a 3+. It wants to become a 3-. Its closest noble gas would be krypton. So we would write this, I'm going to abbreviate and do argon in brackets, 3d10, 4s2, 4p6, and this would be arsenic 3-. How about this one? Which of the following is the correct electronic configuration for the tin 2 ion? So that's tin with a +2 charge. Now if we look at tin and find, let's see, it's got krypton as the noble gas before it, and then we have 5s2, 4d10, so I'm going to write 4d10, 5s2, and then 4p2. Wait, I'm saying 4. 4d10, 5s2, 5p2. And remember, when we become ions, we take off the highest electrons, and we want to take off 2. So we're going to take off that 5p2. So we should have, and again, we would flip that around. And again, we would write it lowest to highest energy. I flipped it here so I could see which one am I plucking off first, because we go from lowest to highest numerically. But here we can see that it's the 5s2, 4d10. How about this one? Which one's the correct for nickel 2 ion? If you look up nickel in the periodic table, we would do 4s2, 3d8. But remember, we want to go lowest to highest N, so 4s2, 3d8 would come before it. We want to lose 2. We're going to lose the highest N. So let's see, the noble gas before it, argon. So it's either got to be this one or this one. So we know it's got to be argon 3d8. How about this guy? Manganese 2+. Hopefully you got argon 3d5. If I looked at manganese, the noble gas before it, 2+, is argon. And then I would write it. Manganese is 3d1, 2, 3, 4, 5. And of course it's in row 4. It's got the 4s2. So again, writing it from numerical 1, 2, 3, 4. We would do 3d5, 4s2. We know this is not energy, right? 4s2 normally would come before 3d5, just like our periodic table. But as far as seeing which 2 electrons are plucking off 4s2, so it would just be argon 3d5. How about this one? Can you guess? The electron configuration argon 3d6 is which of the following? Chromium, rhodium +3, iron +2, or molybdenum, just neutral? Hopefully you got iron 2. If we looked at iron, we would write it again from left to right. We would say 4s2, 3d, 1, 2, 3, 4, 5, 6. And the noble gas before, argon. But if I were to make iron a +2, we would take off that top 2. So argon 3d6 would give us this ion. How about this one? What about copper 2 ion? We looked at copper. Normally, we would say 4s2 3d9. But to see which ions, and again, this would be argon before it, or to see which electrons we're going to pluck off first, remember we're taking 2, and we would take the highest number, so we're going to take these 2 off. So you should get argon 3d9. Which one of these is the correct one for iron 3 ion? Iron, noble gas before it is argon, so we can cross off our kryptons. And then iron, again, if I were to, would it be 4s2, and then 3d, 1, 2, 3, 4, 5, 6. Here I want to take off 3, so we're going to take off 2 of those and 1 of those d's. So we should have 3d5, argon 3d5. You're doing great. Let's do a few more just to bring it home. Molybdenum 3+. Which one is the correct electron configuration? Hopefully you got this answer. If we were to look at molybdenum, the noble gas before it is krypton. Then we have 5s2, and then 4d, 1, 2, 3, 4. And we wanted to take off 3 electrons, so 2 of my highest 5 gone, and 1 from that d, so 4d3, krypton 4d3. Try cadmium 2 ion. Pause. Hopefully you got this. Zirconium 2 ion. There you go. Which of the following elements has 3 unpaired electrons when it is a 2+ ion? You're going to need to draw the orbital box, and hopefully you found that it was cobalt. So cobalt's highest electron row is 4s2 3d7. We wanted it to become a 2+ ion, so we're obviously taking out the 4s2. That leaves us with 3d7. And if I looked at my d, and I had 1, 2, 3, 4, 5, 6, 7. I have 3 unpaired electrons, paramagnetic. What about this one? 2 unpaired electrons when it is a +3 ion. You're going to need to draw the orbital boxes. Let's check back in a minute. And the answer would be vanadium. If we find it, it would be 4s2 3d3. So to become a 3+ ion, we're obviously getting rid of these 2 first, and then 1 of these to make that 3d2. So then I would have 2 electrons in my d 3d orbital, giving me 2 unpaired electrons. We will need to draw these orbital diagrams as well to see which of these is dimagnetic. There is one answer. Which one of these is dimagnetic? Meaning there are no unpaired electrons. And the answer would be magnesium 2+, because magnesium losing 2 electrons gives it the configuration of a noble gas. Noble gas has all paired electrons. How about this one? Which of the following ions is paramagnetic? So there would be at least 1 unpaired electron. So we'll need to draw. And hopefully you got zirconium 2+. All right, the next section that we're moving on to is the atomic properties and periodic trends. Once electron configurations were understood, chemists realized that similarities in properties of the elements are the result of similar valence shell electron configurations. One objective of this section is to describe how atomic electron configurations are related to some of the physical and chemical properties of the elements and why those properties change in a predictable manner when moving up and down groups or across periods. And this goes way back to Dmitry Mendeleev when he was coming up with the periodic table, and when he left holes in the periodic table, and interestingly, he predicted all of these properties from atomic weight, density, specific heat, the formula it would create, the density, boiling point, and then 15 years later, when germanium was actually found, notice the similarities. He predicted it would have an atomic weight of 72, it was 72.59. Density of 5.5, it was 5.35. So we can see these, how the predictions were really close to what was found, and they were able to do this based off of trends. We should be a little familiar with the general periodic trends as far as atomic and ionic sizes, ionization energy, electron affinity, and we'll also be able to look to see the enthalpy variation within a group and across the period on the periodic table. The sizes of atoms actually influence many aspects of their properties and reactivity. Size can determine the number of atoms that can surround it and be bound to that central atom, and it can determine what shape the molecule is. So the size, we can see, normally increases going down a group, and it decreases across the period. And this happens because as we go across the period, these electrons are held more tightly because there is higher nuclear energy. Remember, as we go from left to right, our protons are increasing. So there is greater nuclear energy, so those electrons are being held more tightly because of that greater charge, overall charge. So don't be confused thinking this arrow to the right means it's getting bigger. As we go to the right, the atomic radius decreases. However, it does increase going down. There are larger orbitals. I'm going from 1 orbital to 2 to 3 to 4 to 5 to 6 to 7. When determining the size of atoms, we are actually looking at the atomic radii. So if we were to look at Cl2, diatomic chlorine, the distance between two nuclei is the bond distance. And again, nuclei, we're kind of assuming that it's smack dab in the middle, which is not exactly accurate. But if the two atoms that make up the molecule are the same, then half of that bond distance is that radius of the atom. If we know the bond distance, then the radius, again, can be estimated. If we know bond distances of, let's say, 2 chlorine atoms, I can take half of that. And if I knew 2 carbon atoms, we could take half of that. Anyways, we can find out these radii by assuming that these atoms are touching, and so it is half of the diameter. Another trend that we notice when we are going from left to right across the period is that the effective nuclear charge increases. By doing that, if we were to look at sodium, for example, sodium is in the 3rd orbital, 3rd energy level, and so therefore, to find that nuclear charge, we know that sodium has 11 electrons, so we take our Z, our atomic number, and then we subtract S, which is the number of core electrons. That means everything in 1 and 2. And if I were to add up everything in 1 and 2, which essentially is taking my noble gas before sodium, which is neon, so 11 minus 10, That's my core electrons. 11 minus 10 is plus 1. Same with magnesium. Magnesium has an atomic number of 12, so it has 12 electrons. And then again, I'm going to subtract the noble gas that comes before it. That would be my core electron. So 12 minus 10 is plus 2. So we can see as we go from left to right, my effective nuclear charge increases. This trend, as we see size increases, and so therefore size and charge increases. As we go left, the nuclear charge decreases, or I could say as I go right, my nuclear charge increases. As I go left, my size increases. As I go right, my size decreases. And here's a picture to just show again the atomic radii, that as I go to the right, you can see my radius getting smaller and smaller. Again, those electrons are held more tightly because the nucleus has greater charge, so there's a greater pull attraction. That outermost electron shell is being pulled in closer and closer to the radius. However, as we go down and get bigger, we have added extra energy levels. That is definitely making it bigger. So as we go down and our atomic number increases, radius increases. As I go to the right, again, my atomic number is increasing, but my size is decreasing. In general, again, here's one exception, but in general, my size is decreasing because of that pull of from that greater nuclear charge. Which of the following atoms is the largest? Potassium, rubidium, sodium, or cesium? And aluminum, chlorine, magnesium, phosphorus. Hopefully chose cesium first because it is the furthest down on that column, and magnesium because it's the furthest to the left. The next property we're going to look at is ionization energy, which is the energy required to remove an electron from an atom that's in the gas phase. Energy needs to be supplied or given to overcome the attraction between an electron and the nucleus, right? Electrons are negative, nucleuses have protons in it, so it's positive. There is an attraction holding those electrons in that orbit. So to separate the electron from the atom, energy needs to be applied. So ionization energies are always positive values. An electron that's further from the nucleus usually has a smaller ionization energy. It doesn't take as much to pluck it away if it's far away from that positive nucleus. An electron closer to the nucleus usually has a larger ionization energy. It takes more energy if it's closer, because think of magnets that are closer together. There is a greater pull, a greater force holding that electron near that nucleus. Let's look at magnesium, for example. Magnesium on the periodic table is in the third energy level and the second element there. So to remove one, so that's called our first ionization energy. To remove one of these s electrons requires 738 kilojoules per mole. Therefore, I'm taking it from 1s2, 2s2, 2p6, 3s2, taking away one of those electrons, making it 3s1. So we're just making it Mg+. I'm going to say it only takes 738 kilojoules because we're just removing one of those. Now, to remove another, that's called our second ionization energy. So to go from Mg+ to Mg, this is wrong because we're going from Mg+ to Mg2+ by removing a second. So we are going down to, there should be a 1, 1s2, 2s2, 2p6, 3s1, taking away that outermost 3s, so that we have Mg2 plus, 1s2, 2s2, 2p6. Notice that to take away that next electron is almost double the energy. Now when we have our Mg2 plus should be the atomic notation of the nearest noble gas, which is neon. If I wanted to remove that outermost electron to go from 1s2, 2s2, 2p6 down to 1s2, 2s2, 2p5, that would be Mg3 plus, because I'd be removing 3 electrons at that point. Notice that it takes 7,000, almost 8,000 kilojoules, because that is a very strong held together ion, right? Noble gas, very, very stable. So to remove one of those is a large increase for removing that electron from the outermost valence shell. Here's our general trend that the smaller the atom or ion, the increasing amount of ionization energy. Again, it's harder to pull away an electron when the atom is smaller because the electrons are so much closer to that nucleus. We have decreasing size as we go to the right, so therefore it's increasing ionization energy, right? If it's decreasing size, that means that electrons are closer to the nucleus, therefore harder to pull away. And what I just showed you with magnesium, if we wanted to remove more than one electron, the general trend is that the more you remove, the greater amount of energy is needed. So ionization energy to remove 4 would be greater than 3, which is greater than 2, greater than 1. Why don't you take a second and try to find the largest value of plucking off 1 electron. So that's our first ionization energy is what that's called. Hopefully you found these for the largest values. Sodium, it is the highest in the alkali metal group. Chlorine is the furthest to the right, and magnesium is furthest up and to the right of these 4 options. Similarly, but opposite, we could say, electron affinity is the energy change for the process of adding an electron to a neutral atom to form a negative ion. And in this example, we have chlorine, and we know chlorine really, really, really wants 1 more electron. It wants to become chloride so that it can become like argon. So we have a negative sign for energy, meaning that this process is favorable. The trend increases as you go to the right and up. If you think about it, as we go to the right, so my very far right, not my noble gases, but fluorine, chlorine, bromine, iodine, those are going to be really high because they really, really want 1 electron. And slightly less, oxygen, sulfur, those guys want 2 electrons. They want to become a -2. So they have an electron affinity, but they need 2 electrons. So it's not nearly as high as my halogens that really want 1. So we are increasing as we go to the right, increasing as we go up. And like I said, the noble gases, they do not have an electron affinity value because they are not wanting electrons at all. They're happy, they're safe, they're full. So like I said, similar but different. Ionization energy is the ability to lose an electron, which is an endothermic reaction. So that's ionization energy, I. Electron affinity, EA, measures gaining an electron. Often it's exothermic, but not always. So losing, gaining. Let's go through and do some practice problems. So why don't you take a second to look at your periodic table and see which one has the largest atomic radius. Should be Na. Which of these is arranged correctly in order of decreasing atomic radius? This should be your answer. I hope that you're pausing your video here so that you can actually get some good attempts. Decreasing atomic radius for these samples, pause and try to figure that out looking at your periodic table. Should be your answer. Which would have the largest atomic radius? Compare these elements with regards to the following properties. Who has the largest or most positive ionization energy? Carbon. What about arranging these in order of increasing first ionization energy? So to remove one electron, what about these ones in order of increasing first ionization energy? So to remove one electron. There you go. Which one would have the greatest ionization energy? What about the smallest ionization energy? The one with the greatest size. Which one would have the greatest difference between the first and the second ionization energy? Definitely lithium, because it would be taking an electron away from neon. Neon is happy, it does not want that to happen. What about this one? Potassium, similar to the last one. What about this one? Increasing affinity for electrons. The largest electron affinity. Who wants it the most? Carbon. Which one has the largest radius? Which would have the smallest radius? Which group is expected to form 2+ ions? 2A. Here's a summary of the different periodic trends that we were talking about. And I highly suggest you look at your supplemental materials with practice problems as well as the solution guide and going through the chapter to look at other practice problems that have solutions as well. That sums up Chapter 7.